Hi, my name is Eloise. Cindy and Gerard will be joining us again today as we continue to investigate quadrilaterals. Hi, you two.
It's great to be back, guys.
Hi, everyone.
In the last lesson, we suggested some ideas about shapes that may have surprised you. Guys, can you remember what you said?
I said a rhombus is a type of kite.
And I said a parallelogram is a type of trapezium.
Well, it depends on how you choose to define these shapes.
So you're saying there's more than one way to define a trapezium?
You've got to be kidding. Doesn't a mathematician just come up with a definition and then we learn it?
Well, if we can sort or classify quadrilaterals in more than one way, why can't we define shapes in different ways as well? In this lesson, we're going to compare exclusive definitions with inclusive definitions. By the end of this lesson, you should be able to explain the difference between an inclusive definition and an exclusive definition, and write these definitions for different quadrilaterals. Let's start by looking at some shapes that you know well: the square and the parallelogram. Is a square a parallelogram?
Well, I always thought the two shapes were completely different. But now that we've been classifying shapes in different ways, I'm not so sure. I suppose if we're classifying shapes in different ways, then we could define them in different ways too.
You're right, G. Think about it. A parallelogram has opposite sides equal and opposite sides parallel, right?
I guess so.
Well, so does a square. It has opposite sides equal and opposite sides parallel.
Yes, but it also has all its angles equal and all its sides equal.
Both of you are right. A square has all the properties of a parallelogram and a few more of its own. So let's define the parallelogram as a quadrilateral with opposite sides equal and parallel. Now, using this definition, would you say a square is a parallelogram?
Well, I guess so. A square does have opposite sides equal and opposite sides parallel. And your definition doesn't say that it can't have any other properties as well.
Okay, so using this definition, we can say that a square is a special kind of parallelogram. This kind of definition is called an inclusive definition. In other words, it only tells us what is included, the least that a shape must have. It can have more properties that make it a special case of the definition. We could also decide that we want to define a parallelogram in such a way that we exclude the square. So how could we make sure that our definition applies only to general parallelograms and not to a square?
Well, we need to put in something about what the shape can't have. Like, it can't have equal sides. And it can't have equal angles.
Correct. And it's quite easy to change the definition to do this. We can change the definition to say, a parallelogram is a quadrilateral with opposite sides equal and parallel, but not all sides and angles equal. And that gives us an exclusive definition. You don't just define a shape by what it does have, you also define it by what it does not have, to keep it distinct or separate from all other shapes. Now let's move on and make definitions for another shape. Let's take a careful look at isosceles trapeziums. Here are some trapeziums to refresh your memory. These are all isosceles trapeziums. How would you define this shape?
I will define the shape by finding all the properties first. One thing I already know is there will always be one pair of parallel sides. Otherwise, it won't be called a trapezium.
For the other properties, Maybe we could measure all the sides and all the angles and see what we come up with.
Good idea. I will measure the lines and you measure the angles. Then at the end we'll see what we've got.
Why don't you try this as well and compare your observations to Cindy and Gerard's?
So, what have you found?
Look at this. The other sides of these shapes are equal, so I'm going to make that my second property. Maybe that's why it's called isosceles, because it has two sides equal, like in an isosceles triangle.
Hey, look what I found. Look at the angles. I found on the long parallel side, the angles are equal. And on the short parallel sides, the angles are equal to each other too.
But how do we write that down?
Gerard, the angles you used can be called base angles, but don't get them mixed up with adjacent angles.
So can we say that the base angles are always equal?
Great stuff! You've identified the properties of an isosceles trapezium. We could add more about the properties of the diagonals, but it isn't necessary for getting a definition. So I think you're ready to write your definition of an isosceles trapezium.
Okay, we need to decide what's the least information we need to be able to draw an isosceles trapezium.
I think we need the bit about the one pair of sides being parallel.
And we need the bit about one pair of sides being equal.
And I think we should say that it's a quadrilateral. That way we won't have to explain that it's a closed four-sided figure.
An isosceles trapezium is a quadrilateral with a pair of parallel sides and a pair of opposite equal sides.
Hang on a minute. You didn't say anything about the pair of equal sides being the non-parallel sides. According to your definition, I could draw a rectangle. Have a look. Here is one pair of parallel sides. Now I'll make that same pair of sides the equal sides. Then if I join them up, I've got a rectangle.
Okay, a rectangle does meet all the requirements of an isosceles trapezium. It has one pair of sides parallel, and if you make the same sides equal, you will get a special kind of an isosceles trapezium. When I said it must have a pair of opposite equal sides, I meant that there must be at least one pair of opposite equal sides. But I guess the others can be equal as well.
Oh, come on, Cindy. Are you saying that a rectangle is a type of isosceles trapezium?
You're both correct. The definition Cindy's defending is an inclusive one, since it includes any special kind of isosceles trapezium. At least one pair of sides must be parallel, and one pair of opposite sides must be equal. But there can be more properties. As long as you have at least these properties, you can say a shape is an isosceles trapezium. A rectangle has all the properties of this trapezium, and it has extra properties as well. It doesn't matter that the parallel sides are also equal and the equal sides also parallel. So that gives us an inclusive definition that works. Gerard, you seem to want to exclude the possibility of letting a rectangle be a special kind of isosceles trapezium. That means you want to make an exclusive definition, one that won't let a rectangle be a special kind of isosceles trapezium. Let's see if you can make an exclusive definition.
Well, we can say one pair of opposite sides are parallel but not equal. Then we can say one pair of opposite sides are equal but not parallel. Can I leave out the angles? We didn't use them in any of the other definitions.
Oh, that's fine. So what have you got now?
This is my definition. An isosceles trapezium is a quadrilateral with one pair of opposite sides parallel but not equal, and one pair of opposite sides equal but not parallel.
Right, let's take a look at this together. Gerard, you're saying that if the parallel sides can never be equal, and you'll always get a shape with a longer and a shorter pair of parallel sides, like this, and if you say that the other two sides must always be equal but never parallel, then you'll always get a shape something like this, even though the lengths of the sides may change. Well done, Gerard. You've given us an exclusive definition. It excludes shapes that have more special properties than the ones listed in the definition. It also tells us what the shape must have. So today we have looked at two ways to define shapes using an inclusive and an exclusive definition. But so far, we haven't considered whether these are good definitions or not. We've simply agreed that they are possible definitions, one inclusive, the other exclusive. As your task for today, please work out an inclusive and an exclusive definition for a kite. In the next lesson, we'll consider what a good definition is and see how good these two definitions are. To prepare for the next lesson, discuss the possible definitions for an isosceles trapezium and decide whether you think they are good definitions or not.